Hello, and welcome to this video where I will try to teach you monads in an extremely simplified way. The reason why it's simplified, or extremely simplified, is that we're going to use, or actually follow, loosely, the black box method. The black box method is a method of learning where you don't really learn in depth of the concept of how it works, right? No details implementation, no deep diving into the subject, just how to use it on a surface level. Imagine a black box where you can feed it input and it returns output, right? We know how to feed it input, right? It's extremely easy, but we don't know what happens inside that black box. All we know is how to use that black box to achieve our desired result. And this is kind of the method that we're going to use to explain monads. Now, prerequisites for this is you need to understand that monads is a intermediate to advanced topic, which means that you should know a little bit of Haskell, preferably beginner to intermediate level, and also a little bit of how functional programming works. Other than that, we are set to go. Now, the first step to understanding monads is to understand two concepts before monads, because these two concepts are very importantly linked to monads. You cannot skip these. And these are functors, applicatives, and then monads. So, let's start with a simple example. We have a value. Doesn't matter what value, I just chose 5 because why not, alright? And then we have a function, plus 1. So let's apply plus 1 to this value. As we can see, I applied plus 1 to 5 and it gave me 6. Simple enough. Now what happens if I take that 5 and I put it inside a box? Alright, we take 5 and then we put it inside a context. Doesn't matter what the context is. It could be a wrapper, it could be a box, it doesn't matter. If you want some analogy, you can think of it, if you're in like OOP languages, pretty much like 99.9% of you guys, you can think of it like as a class, an object that contains the value 5, right? It's just a context. It's a box, something. It wraps the value inside of it. Okay, so now let's try to do the same thing, but this time with a wrapped value. As you can see here, you can see that it makes an error. Why is that? Well, the function plus 1 here does not see the value inside of the box. It only sees the box from the outside. Why is that? Well, if you look closer to it, you can see that plus 1 is just the name of the function. It doesn't even matter. But you can see that it takes in an integer and not a box, right? It takes in an integer and not a box and returns an int. And from the perspective of that function, all it sees is the context, right? Whether it's called box, whether it's called wrapper, whether it's called age, all it sees is the type and not the value inside of the type. And that's why it creates an error, right? You cannot add plus 1 to a box because, well, a box is not a number and a number is not a box. Creates a type error. Now, what is a functor? A functor is a type class or a function that knows how to apply our function to this box. How convenient. What the functor does is it takes this box, takes the value out of the box, it applies the function to the value, and returns, once again, our value. So nice and convenient. A specificity of functors also is that they return the value within the same box. So here we are in GHCI. So as I said, you need to know a little bit of Haskell to begin. So you should know what GHCI is, which is basically just the REPL, which enables us to evaluate expressions. So our goal here is to recreate a functor. and also just to illustrate within code our situation that we did before. Now, if we remember well, we had a value 5, and we applied +1 to it, +1 being our function. If I apply 5 plus 1, it returns us 6. Pretty normal. Now, what happens if I have a box and then try to put that value inside the box? If I put that value inside the box, as we can see here, if I just type our variable here, it returns us a box. Now, if I just try to apply +1 to the box, as we can see here, it gives us an error because +1 does not know how to apply itself to a box, but it knows how to apply itself to a number. By the way, you should already know what this bits of code means. It's very basic Haskell, and I don't need to explain it. But just in case, data is the keyword to create a data type, box is the name of the data type, a is a type variable, which represents any type possible, and box is the type constructor, a, which is again a type variable, and we're deriving from show, which enables us to show the value within the type. Also, a big difference that you need to know is that you need to make difference between this box on the left-hand side and this box on the right-hand side. You need to make a difference because this box is the name of the type, and this box is the name of the type constructor. The difference being that this, once again, is the name of the type, and this is equivalent to the constructor in any OOP languages. For example, if we take Java, to create a new object in Java, you need to use the new keyword, which then creates an object. Well, box kind of acts as the same. Now, why is it called box? Well, I called it box because I chose it. The convention in Haskell is that if your type is simplistic, you should use the same name as your type for your type definition. And basically what this means is that box is the name of the function, which takes in a variable, a type variable, which is of any type, and returns us a box. As we can see here, we have a variable, and we created a box with the box function that has a value of 5. Okay, so now that we have our wrapped value, let's now create our functor, because as we've seen, we cannot apply +1 to box. To do this, I will do what's called a multi-line code block. And this, you don't need to do this if you're writing it in a file. I need to do this because GHCI is interpreted, which means that it interprets line by line, but by doing this, I can do multi-line code blocks. This doesn't matter for our understanding of functors. How do I create a functor? Now, functor is a type class from Haskell that is already declared. All we need to do is just to implement it. So I'm going to do instance, which is the keyword that tells Haskell I want to create an instance of a type class. Which type class do I want to? Functor. And what is the name of that type class that will implement the functor type class? Well, it's pretty simple. It's going to be box. Also, box is not a type class. It's just a type. I just misspoke. So, oops, sorry. So then, where is just the keyword for defining something. So instance, I want to create an instance of functor where box is the functor and where. So if we look at the documentation, this is Hackage. This is Google, which is kind of like a search engine for documentation. It's really cool, really nice. You have to use it because it's very useful. So if we look at it, we can see that the class here is functor. And f, what is f? F is the functor, and it takes a type and returns a type. So this is a bunch of mumbo jumbo. We can read it. It's not important for our black box method because it's implementation details. It's details, but we don't want details. All we want to do is just to be able to use fmap. the functor. What's more interesting here is the minimal complete definition. This is what we need to do to implement our functor. And the minimal thing we need to do is to implement the fmap function. If I go to the fmap function, you can see that fmap here in its type definition takes in a function that takes in a type and returns a different type, and takes in a value wrapped inside the functor. Now, if you don't know why f is a functor, it's because in its type definition of functor, you can see that f represents a functor. So we know that in the fmap function, f represents the functor. So basically, we need to implement a function named fmap, which takes in a function, takes in a value wrapped in a functor, and returns a value wrapped in a functor. Now the functor is not necessarily a functor, it's just a context, right? It's a context that it needs to be wrapped in. And let's do that. So we are going to implement fmap, which is the name of a function, f, which is a variable that represents a function. Now, if you wonder why a function can fit inside a variable, that's simple. It's because in Haskell, functions are first-class citizens, which means that functions can be treated as any value, whether it be a variable or just a normal function, which is why f can represent a function. Then we have our value, which will be represented by x, and undefined, which is just a placeholder because we haven't implemented a function yet. So, as we said here, if you remember our example, I said that a functor knows how to extract the value out of the box. Unfortunately, in this instance, functor does not know how to extract the value out of the box because we have to teach it how to extract the value out of the box. The way you do this is that x, we know, is a type, right? Which type? We know it's box. So we're going to pattern match it or extract the value from it, right? So by saying that this x, or now it's not x anymore, it's not called x anymore, is a box, Haskell immediately knows that this value must be a box, and that in a box there's always one type variable, and this type variable is our value. So if I just add x in here, x will represent our type variable. Basically, if you compare this with this, you can see that x represents our 5 in here. And yeah, after that we have extracted the value from a wrapper. All we need to do is just to apply the function to the value. A functor always returns the value within its own context, which means that all we need to do now is just to return the value within a box. To summarize, fmap has a function, has a value where we pattern match it to its type, extract the value from its type, and then take the value, apply the function to it within a box, and we return the box. And then all we need to do here is just to close this. Oops, I almost did the wrong thing. To close this, and there you go. See, no errors. So let's try our operation again. We're going to use the function fmap with a function which is +1, right, which takes in a number and adds a number to it, adds 1 to it, sorry. And then we take in our wrapped value, which is box, and all we need to do is just to apply the fmap to those both values. So if you look at this, you can see that it actually worked. Box 6, right? We took 5, which is within this box variable, +1 equals 6, return 6. Okay, welcome back. So, in summary, a functor is a function that knows how to apply another function to a wrapped value, right? A functor knows how to apply +1 to a box which contains the number 5. Simple. Now, What happens if I also wrap the function inside a context? Now, you're going to say at me first, wait, you can't do that. Well, yes. This is exactly why the prerequisite was to understand or at least know a little bit about the context of functional programming. Because in functional programming, functions are considered first-class citizens. This means that functions will be treated as values, which means they can be fed into other functions, they can be returned by functions, and are treated as values. So +1 here, this function, is treated the same as the number 5 because they're both values. And this is hence why I can wrap my function inside of a context. Great. Now, since both of my values are wrapped inside, let's try to apply them. Now, as you can visibly see here, they are clearly isolated, as 5 does not have any access to +1, and +1 does not have any access to 5, which obviously will cause an error because nothing will just happen. Okay, so this is where applicative comes in. Applicatives, just like functors, knows how to extract a value from a context, which is why it's important to know what a functor is before knowing what an applicative is. The same thing can be said for monads. You have to know what a functor and applicative are and can do before learning about monads, because they are closely related to each other, but they do different things. But to do these different things, they have to know how to do the basics. So, as we said, the functor here knows how to extract a value from a context, but it doesn't know how to extract a value from, a function from a context. And this is what the applicatives completes. The applicatives knows how to do both. It can extract a value from a context, and it can extract a value, a function from a context. And what it does after is it applies them and then returns an output, 6, and then, as we said, the functor here does not return a raw value, it returns it within the box, within the same context as the starting one. So the applicative is no different. It also returns our value within the box. Okay, welcome to the second part where we will be talking about applicatives. Now that you know how applicatives work, we will now implement it or actually just use it. Let's start again by looking at the documentation. As we can see here, applicative has f, and f must be a functor. So this here symbol means that f is a functor and it must be inside here. Or you can read it like reverse to f must be a functor. Now, once again, we have some mumbo jumbo here, implementation details. That doesn't really matter because we are not interested in this. What we're interested in is the minimal complete definition. So as we already know, an applicative is a function or a type that knows how to apply a wrapped function to a wrapped value. So to now implement our applicative, we have to implement two functions. We have to implement the pure function, which takes in a value of any type and returns the value within our context, right? If we look at the example here, pure is the function call, 1 is the raw value, and returns a value with our context, which in our case is just 1. Great. And then the second function, we can either implement the sequential application symbol or the lift A2 function. Now, if we look a little bit closer to the sequential application symbol, you can see that actually this highlighted part is our function name. The parenthesis here means that this sequential application function is actually an infix function. Now, for those who don't know what an infix function is, let me show you. Okay, now, how do we apply a normal function, right? A normal function, you use the function name, and then you have your first parameter, argument, and your second, and so on, right? And then you just apply your function. Well, an infix function is a different form of applying a function. You have your value, right? Your first argument, the function name, and then your second value. An infix function is always a binary function. Binary why? Because there's always two parameters in a infix function. Now, if you look at this quite close, you can start to recognize the shape of this function call. Where have we seen this already? Well, it's pretty simple. If you have used plus, minus, or any other symbol, it is an infix function, right? Even if you look inside GHCI by doing column T, you can pretty much see the type definition of anything you want inside of it. If I use this on the plus symbol, you can see that it returns us the type definition of plus. So as we can see also, if I just apply the function normally, we can see that this is the value, or the first argument, this is the name of the function, and this is the second value, or the second argument. And if I just apply it, it returns me 2. What's cool about it is that if you unwrap your symbol or your infix function within parentheses, you can do a normal function call, right? So this is the name of the function, this is your first parameter and second parameter, and you can just apply it like a normal function. So if we look closer to the type definition of our function here, we can see that it takes in a function wrapped inside a context. In our case, it's a functor, and it takes also a value wrapped inside another context. Well, it's the same context, but you know, it's wrapped inside a context and returns a value wrapped inside a context. You can see that B here is the same type as this B, which means that what we do is that we take this value and we apply the function to it, and we return the result of the function wrapped inside a value. So let's implement it ourselves. This is once again the same instance of GHCI. I have changed nothing, so we will continue where we left off. So we have our boxed value, right? This box value is 5. Now what happens if I want to box in my add function, for example, right? So box, and I'm gonna just put my +1 function inside this box. Now if I try to display it, it won't work because I haven't its implementation details once again, but it doesn't matter. All you have to know is that the add variable has a function +1, which is inside a box. That's all you need to know. Now, what happens if I want to apply this function to the box value, right? I want to apply this function to box. Now, as you can see here, it doesn't work. So the way to make it work is to create a applicative. So to make an applicative, we will once again, I will actually clear the screen so that it's more visible to see. And the way you make an applicative is to create an instance of the applicative type class, just like we did with our functor. So once again, a multi-line block of code, instance of what? Of an applicative. I mistyped it, applicative. And what is the instance of this applicative? Well, it's a box. Where? Then let's look at our implementation details once again. So if we look at this, we see that we need to implement the pure function. So let's do it. The pure function takes in a raw value and returns a value inside the context. So what is our context? Our context is the box. So the name of the function, we have a value, and then we have a value which we will name x, right? And this value here needs to be wrapped inside a function. Needs to be wrapped inside a context. How do we wrap a value inside a context? Well, simple, by creating a box. Box, which is the type constructor and not the type, right? These and these are not the same thing. and we just wrap it inside of it. And that's pretty much it, right? Have pure function. We have a variable or a value called x, and we just return the value x within a box. And that's done. Now let's do a little thing, the other thing, which is a little bit more spicy here. So we know that this sequential application symbol is an infix function. Now there's two ways of defining an infix function. We're going to do it one way so that it's simpler to explain and the length of the video is not too long. So we know that an infix function has a, the name of the function, and b, value, and undefined as placeholder. Simply, now a we know is a function, so we need to extract the function out of the context. How do we do this? Well, we do the same thing as if it was a value, because in functional programming, functions are first-class citizens. And since functions are first-class citizens, we can treat them as values. So as we said, we already know that our context is a box. So Haskell now knows that the a value, which is now just a pattern matched, is a box. And what does a box have? Well, it has a value. So we're going to say function, because we know that the first argument is always the function. We can represent f, the variable, as a function. Then we're going to do the same thing for b. b, we already know it's a value. And in what context is the value wrapped in? We know it's box. So box has a value of x. Now, if we remember it, we need to apply the unwrap function to the unwrap value. So we're just going to do f(x). But remember, an applicative needs to return the value within a box. So that's what we're going to do. We're going to create another box, and it returns now the value applied to the function within a box. And we are done here. Okay, now that we have created our applicative, it's time to use it, right? So, as we said, we have our box value here, which is 5, and we have our function, which is add. Oh, I forgot that you can't display it because of show. Anyways, it doesn't matter. We have our box, which is our value, and we have a wrapped function, which is add. Then what I'm going to do is that I'm going to say, okay, I want my function. If I remember the order of it, it's I need to have, okay, so the function first, function, which is add, sequential application, and box. So we're going to apply the function, the wrap function, to this box, and it will return us 6. And this is how you make an applicative. Great! In summary, an applicative is a function that knows how to extract a value from a context, but also extract a function from said context. They then apply it together and then returns the result within the same context. Great, great. Now, let's talk about monads here. Monads do not solve a general problem like functors and applicatives. They solve more of a specific problems. Where functors and applicatives do work well, they do not chain together very well. And the fact they do not chain together very well leads to problems, or actually just little difficulties in handling other things. And monads are kind of like functors and applicatives on steroids, where it is manageable, or at least more elegant and more manageable, to chain operations together. They do other things, but once again, implementation details, we don't need to know about them for now. All we need to know is just how it works and how do you use it. So let's start with our example here. I have my +1 function, my beautiful function. Let's change it a little bit and call it +1. Now it's the same function, I just renamed it, or actually I just gave it a name, right? +1. Now I can also look inside the function, right? this normal function definition, you can see here that it takes a raw int, and returns a, oh, it doesn't return a raw int. This time it returns a boxed int. Very interesting. Nice. Okay. Now what happens now if I try to apply +1 to my boxed 5? As we've always seen previously, we know that the +1 function takes in an int, a raw int, and not a boxed int. So obviously it throws an error. Okay, so the monad comes in now. The monad here knows how, once again, to extract a value from the context, just like the functor, and then what he does is that he applies the function to the value, just like the functor and the applicative, and then returns the wrapped value. Very nice. And that's what a monad is, basically. In its simplest form, that's what a monad does, more like it. Now, what's cool about this is that this enables us to chain said +1 function. Because if you remember, +1 takes in a raw int. Or actually, the monad takes in a wrapped function, a wrapped value, but not +1. So what we do is that the output of our monad becomes the input of the next monad. So if I chain +1 multiple times together, right? For example, we go, first one is wrapped value, monads unwraps it, and then feeds it to the +1. The +1 takes in the raw value, and then poops out a boxed value, and that's our output. If I use +1 again with the monad takes in the wrap value, unwraps it, feeds it to plus, and then once again outputs the box value. And then you can do this over and over again until you have finished your sequence of, application. And this is how the monad just chains together elegantly multiple computations together. And this is what the monad does. It does not solve a general problem like a functor or an applicative. It solves a specific problem where it is easier to chain together stuff and makes it more elegant. Welcome to this final part where we finally talk about monads. Now, as you know, this is once again the same instance of GHCI because to create an instance of the monad type class, you need to first create a functor and an applicative because a monad is an applicative and an applicative is also a functor and not vice versa. They are extremely linked together, but they do different things. And the reason they can do different things is because they can do the things that the previous type class could do. Anyways, this is just mumbo jumbo. Let's start looking at the documentation. So, to be a monad, M must be an applicative. Simple as that. Cool. These are some laws that you have to respect. But once again, black box method, so we don't care about like nitty-gritty implementation details. It doesn't matter for us. All we want to do is just to learn how to use it. And that is great because in this documentation, it tells us how to use it. So the minimal complete definition is to implement this function. Now, if you look at this function, we can see that it's a greater equals to symbol, and it's enwrapped with parentheses, which means that it's an infix function. Also, this symbol is called bind function. But anyways, the point is that we see that it's an infix function. So great, let's just keep it there. So this infix function takes in a wrapped value, as you can see, wrapped inside a monad, an applicative functor, whatever, it doesn't matter, it's just a value that is wrapped inside a context. It takes a function. Notice that the function is not wrapped inside any monad or any context, right? It takes in a raw function that takes in a raw value, right? A raw value, and returns a wrapped value. And then our function, the bind function, just returns the wrapped value. Let's see here. So the function so we want to apply a function that takes in a raw value and returns a wrapped value. Unfortunately, we cannot, because the value that we want to feed it to is wrapped inside a value. So our job will be to unwrap this value and feed it to the function and then return the output of that operation. Simple as that. Now let's do that. Once again, multi-line block of code, and let's start. So we want to create an instance of what? Of monad. And what is the name of this instance? It's box, where we are going to implement our bind function. Now, once again, the bind is an infix function, which means that we will have A, the name of the function, and then B, our value. And it returns something undefined because we have not yet implemented it. And once again, it is just a placeholder. So, if we remember well, we need to extract the value out of our type. What type it is? Well, we know that the context is necessarily a box. And what does a box contain? Well, it contains a value because it's a type variable. So it contains a value x, which has any type in the world. Great. So we have our value, and then we have our function. Now this function, I will change it to f because this is how you represent a function. And then that's pretty much it for the pattern matching because that's all we need. Great. So now, as we said, we want to apply the function to the value. And then we are done. But then you're going to ask me, wait, I thought monads needed to return a wrapped value, right? Well, yes. But then why am I not wrapping it inside a box? Just like this, right? Sorry, oops. Just like this. Right? Why am I not doing this? Well, that's pretty simple. That's because the output of this function already returns a monad. So if I apply f to x, this function will return a monad, and I don't need to do it myself. Sorry, that's my background. So as you can see here, our function needs us to return a wrap value. But I don't need to wrap it manually because this function already returns the output. See this? See how this output is wrapped inside a monad? Well, all I need to do then is just apply it. And there we go. So I'm going to close this and see no errors once again. Okay, cool. So we have our value, which is 5. We need now a function so that we can wrap it. Actually not wrap it, but just apply it to the monad. So another multi-line block of code, and then I'm going to create a function that's called sub, short for subtraction, which takes in an int, a raw int, mind you, and then returns not a raw int, but a box int. So we have the context, it returns the context and returns the type of the context. Takes in a raw type and returns a wrapped type. Okay, so this sub function takes in a value parameter, and then we're going to return a box with value -1. And there we go, this is done. This function is done. Once again, no errors. And now, let's try to use our sub value, our sub function with our box value. Remember, this will fail because the sub function takes in an integer and not a box. What is our box? Well, it's a box that contains 5, but not only 5. So to do this, let's use our bind function. So we want the value, or is it the function? I don't remember the order. Okay, so yeah, we take the value, which is box, then we're going to push it inside the sub function. right? Imagine that we're taking the box value and then we jam it inside the subfunction, forcing it into the subfunction, even though it's wrapped. So instead of gracefully unboxing the value, we are jamming the value inside the function, and then once the box is broken, the raw value is then revealed to the subfunction, and the subfunction can use it. Now, if I go on with this operation, it will return to me 4. And that's exactly what it needed to do, right? Box was equal to 4, and I did the subfunction which removes 1, and it gave me 4. Now, what's cool about this bind function is that you can loop it. Now, what do I mean by this? Now, look and see what happens if I try to bind multiple operations together. It will return to me 2. Now, why is that? Remember, first time is that sub could not be chained because it needed to take in a raw value. Our value here is not raw, it's inside of a box. What does the bind function do is that it takes in the box, unwraps it, and feeds it to the function of a raw value, right? We unbox the box value, takes out 5, and then feed 5 to the subfunction, which then returns a wrapped value of 4. Great. Now, here's the important distinction. So what would then happen if the subfunction did not return a wrap value? Instead, it would return just an int, like a normal int. Let's look at it. So box is a wrap value. We feed it into the function, unwraps it, and now towards this point, box is unwrapped and reveals 5. We feed the 5 inside the subfunction, and now instead of returning a boxed int, we're going to return an unwrapped int, right? A raw int. So 5 minus 1 is 4. So towards this part is 4, because we said instead of returning a box, we would just return a raw value. Okay, now I try to chain the output 4, raw 4, with another bind value. Remember, the bind value only takes in boxed-in values. Unfortunately, this subfunction returned a raw value. So 4, which is raw, cannot get into the bind function since it's not wrapped in. So why we can bind these functions is because the function we used returns a boxed value. And so basically the output of sub is the input of bind, and bind takes in a wrapped value and enables us to chain it. And this is basically how monads work.